world of hydrocarbon extraction is a highly dynamic and competitive environment, so staying ahead of your competition isn't just an advantage, it's a necessity. This video is for highly ambitious cannabis extraction teams that want to take their craft to the highest level and lead in this evolving market. We'll explore advanced techniques that are reshaping the industry. We'll cover some of the design flaws that exist in the vast majority of closed-loop extraction systems in use today, and how you can make some critical changes that will at least double your performance of your existing system. Then we'll dive into how extractors are implementing cutting-edge crystallization techniques directly into their closed-loop extraction process. This tech for THCA isolate can dramatically improve your facility's efficiency and output. This video is not just about keeping pace, it's about leading the charge in a fiercely competitive market. If you want to discover the strategies that separate industry leaders from the rest of the pack, then stick around for the full video. Let's dive in. Okay, we're going to talk about some of the constraints associated with the conventional design of hydrocarbon extractors. And typically, that conventional design is associated with using a compressor to recover the solvent. Why is that a constraint?
Yeah, so active recovery, really came about because it was easy to do, and for smaller systems, it worked well. It was easy to predict, how the system was going to behave, and easy to recover solvent without having a really good knowledge of vapor pressure. But ultimately, the compressor pump doesn't scale well, and it adds energy to the system. It makes it more challenging to go to an industrial scale.
Right, because if the only way to scale up how much vapor a compressor can recover is by making a bigger compressor.
Yeah, so we definitely used to see back in the day, big walls of Haskell's to achieve that purpose, but that's not really an efficient way to scale. And really the compressor has this limitation that it can only displace a certain volume of gas. And so like you said, buying multiple compressors is the only way out, or the only way to increase your scale.
Or even, really large compressors. We saw that kind of trend for a little bit, but there's a challenge associated with that as well. And the main thing is that everybody has a limited amount of space in their C1D1 booth. And, the other thing is that the compressors are pretty loud. So you make a bigger compressor and you're increasing the amount of noise pollution in the space as well.
Yeah, definitely not an appealing thing to have multiple large gas compression pumps going in a booth. In our opinion, it's much better to have larger heat exchangers and a larger chiller external to the booth and switch to passive recovery.
Mm-hmm. So when we're looking at the constraints associated with the design of conventional hydrocarbon extraction systems, a lot of the commercial systems, like the first iteration, the first cohort, so to speak, of commercial systems all used a gas compressor. And there's some major disadvantages to using a gas compressor when you're trying to scale it up beyond that initial scale. Want to just tell me a little bit about some of those challenges?
Yeah, absolutely. You kind of end up a little bit stuck when you're trying to scale up and using gas compressors, because the only way to increase your solvent throughput is to buy multiple of these compressors. And that's expensive, and it adds a lot of energy to the system that you don't really want there. It adds a lot of noise, and it takes up a lot of space in the C1D1 booth.
One of the big problems associated with using compressors is obviously the heat that gets added to the system through heat of compression.
Yeah, so the problem that you encounter when you're trying to scale up a system using gas compressors is that you are adding an enormous amount of heat to the system by compressing the gas in order to condense. And ultimately, if you're just trying to chill your solvent back down to perform another extraction, that's actually really counterproductive, because you need to remove that heat that you're putting in order to condense the gas.
Yeah, the other big problem that I see in pretty much every facility I go to is there's a limited amount of space in the C1D1 booth as well. Like C1D1 booths are the most limited and most constrained operating space in any facility, essentially.
Yeah, so that can be a challenge when, a lot of facilities have a 20-foot or even a 40-foot booth. Your real estate is very limited. And so if the way that you're scaling up is by adding more and more compression pumps, you're going to run out of space really quickly.
The other thing that I see happen in the process when people are using the recovery pump is all of a sudden they get halfway down the recovery, and because you're pulling vapor from the collection vessel, the temperature of the collection vessel starts to drop. And then you get low vapor pressure going into the pump, and the whole process kind of grinds to a halt.
Yeah, absolutely. And this is why people, started adding propane. In some cases, started adding propane to their system was to keep their vapor pressure high throughout the whole process. Because what's happening is you're gradually shifting towards a higher ratio of butane in your collection pot. You're flowing down that way. And then to your point, if you don't have enough heat being provided to your collection pot, that heat of evaporation as it's leaving is going to drastically cool everything down and then slow it down. And that's challenging as well.
Yeah. The other thing that's associated with that is that, a lot of these systems, conventional systems in that 100 pound per day, 200 pound per day range, they're using little recirculators, lab-based heated circulators. And, they've got tiny little pumps on them. Mm-hmm. They've got some of them get up to about 7 to 9 kilowatts, but most of the ones that I see are about 5 kilowatts. Mm-hmm. What are some of the challenges that causes?
Yeah, so really the entire system needs to be balanced in the sense that you need to have a sufficient amount of kilowatts provided to achieve the extraction rate, the recovery rates that you want, but you also need to have the circulation speed to be able to keep up with how much heat is being pulled out of your heatings.
So it's a gallons per minute constraint there. The pump on that little lab heater just can't keep up with the amount of kilowatts of heat that needs to be delivered to the collection vessel.
That's exactly it. Yeah. So you'll have your heating fluid will be returning extremely, extremely cold because it's just circulating too slowly, even if you have sufficient kilowattage in that heating system.
And then one of the things that I actually see people do to counteract that is they start cranking up the temperature.
Yeah.
But ultimately that really does nothing because it's just a short-term fix. It's really the amount of energy and not the temperature that is the constraint.
Yeah, and you can squeeze a little bit more by having a little bit of a higher delta T on the inlet of your jacket, but ultimately the solution to the problem is increasing the flow rate of that heat circulation.
The other thing that's kind of an issue with these things is they have reliability issues sometimes. And if you don't maintain them, then they can break down. A breakdown in a key component like a compressor, if you're relying on that for your extraction process, and then all of a sudden it's out of service, your entire facility essentially grinds to a halt. And that can be very, very expensive. So a lot of times what people will actually do is they'll have a backup. And that's also, if you're going to have a $20,000 recovery pump, then you also need a backup. Mm-hmm. You're looking at pretty comparable costs from CapEx perspective to just replacing it with a better solution.
Yeah, the compression of gas is a pretty intense process in the sense that you have this piston that's applying a lot of force to the gas. You have these seals, you have sliding components, you have one-way directional valves, you have and the PRVs. You have all of these things that can go wrong, and so simplifying that to a heat exchanger that just has a gas condensing on it removes a lot of risk from that.
So there's no moving parts.
Yeah, exactly.
Right? It's or you're externalizing those into something that's a little bit easier to maintain, like a chiller. The other thing about these compressors is that it's a specialized piece of equipment. There's not a lot of technicians, in various parts of North America that understand how to work on these, have the parts available. If you're replacing that with a chiller that's just condensing, like in a passive recovery scenario, chiller technicians are everywhere in North America, everywhere in the world. Yeah, people can service chillers.
That's right. And chillers are kind of, it's a different style of compressor inside of a chiller typically, especially on the industrial units. And they're very robust and, there's a lot more of them out there kind of thing. And those compressors are ultimately a lot more reliable in the chillers.
The other thing is that they're outside of your room. So they're not taking up any real estate in the most valuable part. And we recommend outdoor chillers as well. So you're not actually rejecting heat into the facility. A lot of our customers, we actually see them putting chillers indoors, taking up valuable real estate, even if it's not in the C1D1 booth, still rejecting the heat from your process into your building. Now your building's HVAC system's got to deal with that.
Yeah, exactly. You have to have the makeup air, adjusted to be able to account for that. And a chiller outside really is a fantastic solution because it's very easy to pipe those chiller lines through the wall.
Yep. Another major constraint in these conventional hydrocarbon system designs is the amount of time it takes to cool the solvent back down to the extraction temperature. A lot of our clients, ideal extraction temperature is between -40 and -60. You only have a limited amount of surface area to cool that tank back down. So, only a small fraction of the solvent inside of a tank is actually in contact with the jacket, and that can be a big limitation. Any other limiting factors there when it comes to kind of re-refrigerating your solvent?
Reducing the temperature that your solvent is returning at is kind of one of the first strategies that people use, and that comes down to the passive versus active conversation, where if you're recovering passively, typically your solvent return temperature is a whole lot colder. And that'll make things easier to cool down, getting ready for the next extraction.
So in an active recovery, you're using a compressor to compress the gas, heating up the gas before it condenses. Now you have to take that heat out of the system. In a passive recovery, explain what's the difference there.
Yeah, so essentially you're condensing at a lower temperature, and you're using temperature alone, and you're not adding any compression force or any additional energy to the system. And so often you'll be condensing at a lower temperature. You'll be returning at, say, -20 as opposed to 20 degrees Celsius often on the outlet of that.
The other thing that comes with pretty much every conventional hydrocarbon system in this capacity range is the low temperature chiller. Super expensive, very high quality build, really great engineering, but maybe not really the right tool for the job, because a lot of the time these chillers, they only have about 1 to 1.5 kilowatts of cooling capacity at a very low temperature. So there's kind of this gap that you experience where it doesn't have enough energy, but it does have enough, it does have a low temperature cooling capacity. Can you explain the difference between those?
I think in a lot of lab applications or analytical applications, you want a chiller that will get to a really low temperature, maintain it, and then have a lot of data collection capacities, and that's good for that application. But really, when we're talking about condensing solvent, we're trying to use something that rejects as much heat as possible, not something that necessarily goes as low as possible. And so they're kind of different optimizations.
Another design issue with some of these smaller systems is these really narrow collection vessels, some of them 6 inches or even 8 inches wide. What happens, when you're trying to push the limits of those?
Yeah, that's an interesting kind of hidden problem that we see in a lot of systems, with essentially a boil over phenomena, where when you go really narrow and you have you're boiling off your solvent and the liquid is becoming more viscous, the bubbles will grow and grow and grow, and then eventually escape out of the top of the collection pot because it's too narrow to essentially have a rolling boil.
So you have this foaming effect, and the foam is just rising and getting closer and closer to the top.
Yeah, exactly. And so you have this unfortunate need to throttle the gas flow out of the collection pots, and that's really counterproductive to trying to recover your solvent as quickly as possible.
So the conventional closed-loop hydrocarbon extractor design uses nitrogen to pressurize the solvent tank, create a pressure differential, and get that liquid solvent to move into the extraction process from the solvent tank. What are some issues with that hold back people's extraction rates?
I think that is a good tech in the sense that it allows you to do passive recovery, but it comes with this challenge that you have to spend time off-gassing your nitrogen at the end of every push in order to return the solvent back to the solvent tank. So if you're adding a head pressure to your solvent tank and then pushing it through, you have to then relieve that pressure, or else the gas cannot return back to your solvent tank. And so that poses operator risk, because you're off-gassing nitrogen, which often will have butane and propane mixed in it.
Well, you're losing some of the butane and propane every time you do that as well.
Yeah, exactly. There's a consumables implication to it. And then it's also harder for operators to run that. It adds complexity where they're monitoring their pressure, and then they have to remember to do that, and then it takes time. But the biggest issue with it really is that it halves your total recovery, or your total throughput, because you're pushing your solvent through for 50% of the time, and then you're off-gassing, and then you're recovering for 50% of the time. It's much better typically to be extracting 100% of the time.
Right, so if you can eliminate the use of nitrogen from the extraction process, you can eliminate the need to off-gas, and you can run columns continuously, meaning you can recover vapor continuously. And so both of those processes can happen simultaneously, meaning that you're running continuously all day long until the end of your shift.
the goal should be to never stop extraction, right? You should always have a consistent flow of solvent running over biomass at every point, because then it's a continuous, maximum throughput system.
And that's really where you get to peak performance.
Yeah, is honing in on, adjusting the parameters to maximize that throughput rate, but keeping that extraction rate continuous.
Right, so once you've eliminated all those bottlenecks, then you get to pretty high level of performance. And that's where even having 3 or 4 columns, like most of these extraction machines come with, even that becomes a bottleneck. And reloading columns is really, it's a good problem to have once you get there, but you can break through that as well. And that's usually where we're helping people at this kind of a second level of performance increase.
We often say that you kind of want your columns to be your bottleneck, because that means that everything else is right-sized for the extraction that you're doing. And, loading and unloading columns right now, unfortunately, is a very, human operator intensive element. And so it's functional. It makes sense for that to be your bottleneck.
What's a good speed at which you can crank through columns if you're really hitting top performance on a hydrocarbon system?
If you have a constant flow of solvent going through your system, we try and aim for, between 5 and 10 minutes per column. And that seems to be a reasonable amount of time for somebody to open and then safely close a 6-inch column and swap your material.
So once an operator has alleviated all those prior bottlenecks, like you're going passive, you've eliminated the compressor and all the other bottlenecks, then you really get to a point where the reloading columns becomes the main challenge and the main constraint for how fast you can extract.
Yeah, exactly. And that's a relatively easy problem to solve. You just add more columns. But I also think that, how fast you can pack columns is a natural bottleneck, and that's an acceptable bottleneck to have, really, to match your desired extraction rate.
What's a good rate at which you should be able to turn over columns if that's now become your bottleneck, where solvent recovery is basically, you can recover solvent as fast as you can use solvent?
Yeah, so we like to think of it as a column should take around 5 to 10 minutes, and you should have your solvent recovery should be going at the same rate that you're feeding more solvent through those columns. And then that's roughly how long it takes to be able to switch a material sock out and then undo and do back up a 6-inch or an 8-inch tricline safely.
So it sounds like a good problem to have when, turning over columns is your main bottleneck. When you're turning over a column every 5 to 10 minutes and you got a 6-column system, what kind of throughput numbers are we talking about here?
If you're turning over a 2-kilogram column every 10 minutes, you're going to be extracting about 12 kilograms every hour.
It's about 25 pounds, 30 pounds an hour.
Yeah, 30 pounds an hour. But that we see possible with a 3-column system. You can often get to around double that with a 6-column system. So you'd be at around 50 to 60 pounds an hour.
Any ideas for once you get past that, for operators that are really looking to hit huge numbers, mass scale processing for an entire state, and really becoming a market leader at a national or potentially even international level? That's where that really starts to become that bottleneck. Can you hint at any potential solutions to that?
In other extraction industries, there's nobody that are loading and unloading material socks out of really small columns. All of them have moved to really large scale processing, biomass processing tanks. And, often you're using powder transport systems to load the tanks. You're using various, flushing techniques to be able to purge all of the solvent out of your tanks. You're using, again, powder transport or liquid to unload the biomass out of the tanks. And, moving towards a completely automated system where you don't really have an operator involved at all is typically the way that, large-scale material transport and extraction systems tend to go as you scale up.
So the last constraint that we'll talk about when we're talking about hydrocarbon extraction processes is the fact that pretty much all these conventional systems, you open a valve and outpours crude oil, but that crude oil needs further processing to get to a final product. What kind of innovations are available now that solve that bottleneck?
Yeah, so we're actually pretty fortunate in cannabis extraction that our we can perform an isolation with our extraction solvent. So, by using butane and propane to perform that crystallization at the end of your extraction process, whether in your existing reaction vessel or in a separate crystallization vessel, you can essentially pour the isolated product out of your system directly without too much additional post-process.
So rather than pouring crude, you're pouring pure 99% THCA and a high terpene extract, and then you're right down to your base ingredients, and formulation is the next step, but you have one continuous process that goes right to an isolated end product.
Yeah, exactly. So you are able to, at the end of your extraction process, you're able to crystallize out, your most desirable compound, THCA, relatively easily, and then you can eject it from the system, as you said, as a base ingredient.
Now that we've covered most of the constraints that are associated with, the conventional hydrocarbon extraction system design, primarily the compressor seems to be a limiting factor. How do we go about removing the compressor from the system and creating a passive recovery for our process?
And to be clear, often we will leave the compressor involved in somebody's system, but more as a utility function. It's a convenient tool to have, but for the bulk of recovery, we'll switch over to a passive system, which entails a large heat exchanger and ensuring that you have sufficient heating and cooling to support the system.
So the heat exchanger is for the solvent vapor condensing function, and then you have a additional heat load that's being added to the vaporization function as well, right?
So let's use about 1.5 pounds a minute as kind of a boilerplate maximum for a lot of these compressor pumps. Right?
Pounds per minute of solvent vapor condensing.
Yeah, that's right. You can easily get to 5 pounds a minute, 10 pounds a minute with passive recovery by using a big heat exchanger, plate or shell and tube, to be able to reject all of that heat of condensation. But you need to have the chilling capacity in order to support that. And then as soon as you add that chilling capacity, you're going to really be sucking a lot more heat out of your collection pot. So you also need to have the heating capacity available to be able to support that.
You're making alterations to a certified system. I just want to make it clear for our viewers that you make sure you consult a professional engineer when you're doing this. This is something that we've helped a lot of companies do in a safe way and compliant.
Yeah, there's a component to it where we're evaluating the heat and mass transfer within the system, where we're ensuring that all of the, your condensation loads, your chilling of your solvent loads and your heat loads are all balanced out for your throughput. But then there's also a safety component where you're ensuring that all of the pressure components are properly registered and compliant to your process flow.
Yeah, and then there's a third party that will stamp that and evaluate to make sure that nothing gets overlooked.
Yeah, exactly. As the manufacturer, you often have to have a third party to review it, especially, in the States, it's a third party engineer. In Canada, it's an accredited, the TSA or TSC, and they will review the system as a whole.
And one of the really cool things about a system like this is if you do balance that load correctly, you're just operating at almost no vapor pressure, because the solvent vapor in the system is condensing at the exact same rate that it's evaporating.
Yeah, we use that for a metric of success. So the system is operating really, really smoothly, is that you have the same pressure in your solvent tank as you do in your collection pot, and you can hear a whistle of the solvent gas flowing back to that solvent tank extremely quickly.
That's actually one of the other constraints that get solved when we're dealing with these passive systems, is really, really big vapor piping.
Yeah, you don't want any back pressure on your collection pot, because then you're fighting it by increasing temperature and whatnot. Really, you want to have a large bore gas line to be able to handle the, many, many pounds a minute that you're recovering at.
Super high vapor flow rates.
Yeah, exactly. The machine should whistle when you're going full speed.
So that opens up another question about, the constraints around adding nitrogen to your system. So if you are no longer adding nitrogen to your system, there's no pressure anywhere in your system, then how are you moving liquid around?
Yeah, so what we're doing is we're using liquid diaphragm pumps to be able to pump cold solvent through the system. Butane is really interesting in that it is, very low viscosity and also very prone to cavitation because it has it's so easy to vaporize it. And so we use a specialized pump that's rated for cold temperatures and can pump really thin liquids. And we're drawing solvent from our solvent tanks and then pumping it through our columns individually, which is very fast because you can pump 500 liters an hour really easily with one of these pumps. But also it's very predictable and very easy to understand for an operator.
One of my favorite parts about it is it also solves the constraint of chilling the solvent that's in your solvent tank. When you have a full tank of solvent, a very, very minimal amount of liquid is actually in contact with the jackets. And so how we solve that, it's actually kind of the same solution, is because you have that pump, you can now recirculate through a plate heat exchanger to remove heat way faster. And so if you have a minus 40 chiller that's hooked up to that, you can drop the temperature of 150 liters or 30 gallons of liquid in just a few minutes.
A jacketed tank is effective at cooling, but it takes too long because you don't have movement along the sides besides the natural convection of the solvent. You have this boundary layer where you have cold solvent slowly descending, but it is really nothing in comparison to pumping your solvent through a cold plate exchanger where you have an enormous amount of surface area and then transferring it back to the tank so you get that turnover within the tank. You can, shorten your cooling time for your solvent drastically.
That effect doesn't really translate to the evaporation side because you've got the boiling effect of the butane. And so you've got this kind of recirculation that happens naturally within the collection vessel.
Yeah, when we look at, turning on an agitator to try and speed up a collection pod, it doesn't actually have a huge effect. And that's, to your point, is there's so much turbulence already within that and so many currents going within that solution as those gas bubbles are formed that you have really good contact to the surface area in your collection pod.
That also brings up another constraint. Some of these smaller systems, they have a narrow, tall collection vessel that, like we mentioned earlier, it kind of sends these bubbles shooting up to the top of the collection vessel.
Yeah, so really the solution to that is relatively simple. You just have wider collection pots because what you're trying to overcome is the fact that the surface tension of all those bubbles is such that it's going to rocket out like a chimney. But if you have a wide enough collection pot, you can actually get turnover and create a rolling boil where the level isn't rising as you increase your boiling rate.
And it's also mixing up the solution as you go.
Yeah.
One of the things we talked about as a constraint was these really low temperature chillers, very high precision. They've got the ability to go minus 60 or even sometimes minus 80, but they don't have a whole lot of kilowatt heat removal. How does that fit into the equation when you're going from an active compressor-based recovery to a passive recovery?
Often when we're talking about switching clients over to passive recovery, we're kind of using a chiller that's optimized for a different function. So we'll often have a chiller that is either they already own or that we suggest purchasing that is optimized more for total energy rejection. And then we're handling, and that's going to be focused on the condensation of the solvent. And then we've got another chiller that will be focused on the chilling of the solvent and getting it back down to extraction temperature.
And that chilling process, if the condensation is happening at 0 or minus 10, that really low temperature lab chiller really doesn't have a whole lot of work to do. It's only going from minus 10 to like the extraction temperature. Typically, clients are using minus 40 to minus 60 as kind of the general range.
It's interesting that it takes a lot more energy to condense let's say a liter of solvent. It takes a lot more energy to condense it than it does to bring it down to extraction temperature. And so you can kind of separate the functions and optimize for different things with your chiller selection. So when you're talking about a chiller that is just rejecting as much heat as possible at around 0 to minus 10, maybe getting close to minus 20 to be optimized for condensation, it's a much more efficient chiller and it's a much lower cost per kilowatt. When you get into temperature or chillers that are designed to be able to achieve low temperatures, you're sacrificing efficiency by being able to get to really low temperatures. Luckily, it takes less energy to cool that solvent down before extraction.
So these chillers for condensing solvent, let's say, in the 10 kilowatt to 30 kilowatt range, you're really just dropping the temperature very little. You're going like from, maybe it's 10 degrees Celsius down to minus 10 degrees Celsius, not a huge drop in temperature, but huge amount of energy being removed from the system. And the cost of these chillers, they're very common. And because a lot of applications in, industrial world, use a chiller that is in that temperature range. And so, you're talking about a chiller that's like somewhere between $20,000 and $50,000. These chillers do not break the bank like the really low temperature chillers do. But also the low temperature chiller, once you've added that function, now the low temperature chiller can really shine because it's not keeping up with all this extra heat from the compressor. It's really just taking that condensed cold solvent that's already chilled and is bringing it from minus 10 down to minus 60.
Yeah.
So clearly passive recovery is where the market is going and really been getting a lot of uptake from people that are leading the market. The other thing that market leaders are really focusing on right now is innovative ways to get to THC isolate.
Your throughput was your main constraint in regards to primary extraction, but now success is often measured by how many kilograms of isolate that people can produce or how much they're able to get out the door. And so we're seeing a shift in focus towards isolation capacity being the most important metric.
And usually the first step there is centrifuges, maybe crystallizing with using the centrifugal force to increase the pressure and get that crude to crystallize.
Yeah, often people are, outputting their crude into either miners or Pyrex or jars, and what they're trying to do is crystallize and isolate the THC that way, but you're limited in scale and capacity to do that.
With those kind of solvent recovery rates up to 10 pounds a minute, it's just a no-brainer switching to a passive recovery system. But really the next thing that becomes the limitation is the post-processing. So how are people, a lot of time doing their post-processing now to get to like an isolate and a high terpene fraction?
Yeah, absolutely. So if you're, really churning out crude, that's good, but ultimately you need to process it before it can make its way out the door as a retail-ready product. And so scaling up your THCA isolation capacity and rate is very important because then you can make all your downstream products at the rate that you can sell them ideally.
What most high performance teams are doing now is they're focusing on more extraction as like an ingredients manufacturing process. And then that separates the extraction part of their manufacturing from the actual formulation and packaging aspects. That increases the performance of the system as a whole.
You end up with a lot of efficiencies and kind of a lower risk processing regimen when you do ingredient-based manufacturing. Because all of a sudden you have, your outputs from your extraction system are ingredients that can be recombined by formulators to be able to produce whatever product you want, as opposed to, the current state of the industry in a lot of cases where you have your head extractor trying to produce a specific product out of biomass that he or she has little control over.
And so I think a lot of extractors have figured this out, that they can achieve higher performance by going to isolate and high terpene extract. What are some of the techniques that people are using to, the rudimentary kind of entry-level techniques that people are using to get that process done?
And crystallization is achievable in a bunch of different ways. I think what a lot of folks are doing is they are crystallizing in Pyrex or diamond miners, and then they're separating the HTE pretty manually by centrifuging it or pouring it off, doing recrystallizations. And that works pretty well, especially for, smaller scale operations. But really, when you try to industrialize, you need to be producing isolate en masse. You need to be doing, 10 to 20 kilogram batches. And so you are typically scaling up to an industrial crystallization solution.
So taking the approach where you really look at THC and terpenes as the two kind of core ingredients for all products is becoming really popular, and especially for high performance cannabis extractors. Why do you think that is?
Well, you just have control over, the textures and the value of the products that you're creating, and also you can kind of maximize the value stream, right? So THCA is not unique to a high quality cannabis. You can get it from lower quality biomass, and then you can often, stretch the value of your HTE to many more SKUs, many more units by recombining ingredients.
Right. You can also take a little bit more of like a just-in-time manufacturing approach, can't you?
Back in the day, it was very challenging if somebody wanted shatter, and then somebody wanted diamonds and sauce, somebody wanted pure isolate. And so if you have, THCA and HG on the shelf, you can recombine them to make really any product that you want, depending on what what sales are doing well, as opposed to trying to formulate it at the onset and then having it in storage as those final product forms.
So in one practice might be like trying to source the biomass that will produce the product that is in demand and going straight from biomass to product, being option A. Option B would be sourcing all the biomass, running all the biomass that you can get your hands on, getting everything right to isolate. And then the HDE fraction, some of it you preserve as a really high quality terpene fraction that can be used in multiple different products, from let's say vape cartridges to reconstituting dabbable, even caviar. And then the second HDE fraction from some lower quality biomass might actually get reprocessed into just THC, and the value of the actual terpenes might be very little, and you just end up turning it into distillate, but you maximize how much THC comes out of that HDE. And then all of those three ingredients, you've got high quality HDE, distillate, and THC isolate. You can recombine those as you need them for whatever the market's demanding.
It used to be that if you wanted to make a really stable shatter, you would go speak to the grower and ask them to, chop down a crop early. And that's just not really a functional process. Right now, you've got, irregardless of the biomass coming in, you can pull out the THCA. If it's a nice terpene fraction, you can designate it for your higher value goods. And then you have your operators, which with a much simpler job. They're just focused on keeping the extractor running as fast as possible. And then you have the formulators really deciding what's going out the door.
And the extractor is always producing the same exact product.
Yeah.
They're producing isolate and HDE every single extraction.
Yeah.
There's no exceptions.
Yeah, exactly.
The other thing that's really cool about that is that you can be really opportunistic when it comes to procurement of the biomass.
Yeah, you can essentially buy, when there's a biomass production glut, you can buy really inexpensive biomass. And then also, on the other side of it, if you have a whole bunch of THCA in storage and the prices are increasing, well, you can take advantage of that as well.
So this video is really for people that are seeking market leadership type of approach to processes like this. So that's the point where you really want to be looking at things like purpose-built crystallization reaction vessels, or a series of reaction vessels. And we actually have some vessels like that here. So let's go check it out.
All right.
Okay, so now we made it to the Genome Technology Center, and we're standing with the 2-vessel crystallization reaction system. Lyndon, how can a system like this be used to reach peak performance for solvent recovery and crystallization functions?
In regards to solvent recovery rate, you've got 2 jacketed vessels with heating fluid flowing really quickly through them. And so as your micella is coming from your extraction process, you're able to really quickly recover the solvent from your micella stream, because you have really large surface area, you've got wide bore gas lines, and you've got ample heating systems to keep up with it.
So not just high velocity of thermal fluid, but you're also adding a lot of heat, right? Like somewhere between 15 kilowatts and 30 kilowatts with industrial heating.
Yeah, exactly. Everything with this is to support industrial scale processing. So you have really large ports on the jacket so that the fluid can transfer through really quickly, and also the jackets have a really large surface area internally, so you can transfer that heat into the micella and boil off your solvent.
So you got a 2-vessel system here, and this could be put downstream of an existing hydrocarbon extractor. So it'd really be 3 vessels, right? You'd have a collection vessel, then you have your first reaction vessel, and then your third collection vessel. And that can really optimize performance with 3 vessels.
Yeah, exactly. So depending on what your existing throughput is on your system, you could want to increase your solvent recovery rate, in which case you'd be using both of these as collection pots. Or if you're already satisfied, you're already producing enough crude, then this can be just a designated crystallizer.
And when you have 3 vessels, you can actually extract crude and do a crystallization at the same time.
Yeah, exactly. So you can be continuously producing your crude over the extraction system and then performing crystallizations, which is inherently a batch style process at the same time.
So let's say you're using this as both a solvent recovery skid and a crystallization system. You're switching from one to the other. First, you get the collection and you get all the vapor off, and then you're concentrating that crude down, and you can start a crystallization process. What does a crystallization process look like on something like this?
Yeah, so you would be, performing your extraction, you'd be removing the solvent and concentrating it down, as you said, getting it to, the saturation point where crystallization would be possible.
So when you're running a 2-vessel system, first you're collecting all the solution in these vessels, you're reducing it down, then you're kind of consolidating those into one, with some crude in it, and then you're running the crystallization. Run us through how that crystallization takes place.
So once you've recovered your solvent and you've gotten the solution nice and thick and saturated, you're going to cool the jacket down. This vessel can switch from heating mode to cooling mode. You're going to cool it down and follow a nice slow ramp to try and produce large flocculations of crystals and crash out all the THCA in solution. Then from there, you're going to wash those crystals while keeping everything super cold and transfer all the HTE from this vessel where the crystals were formed into this vessel where you can recover the solvent from the HTE.
So essentially there's a washing process after the crystallization is formed that collects all that terpene extract and deposits it in this vessel so that you can then concentrate that, and the end result is pouring off terpenes right out of the machine.
Yeah, exactly. So we've got this agitator on there, and so after the crystals have formed, we are able to put in clean solvent, cool everything down so that we're no longer dissolving the THCA, wash them off, and then let them settle out and transfer all of the HTE over to this vessel.
So if you're at the scale where you're producing hundreds of kilograms a week, and it really becomes a challenge to filter out all of that THCA out of the solution, doesn't it? So that's where we kind of bring in some heavy duty filtration equipment.
Yeah, exactly. So we kind of have two ways that we'll run a crystallization. Often if you're doing the smaller batches or only a few batches a week, you'll perform the crystallization in there, you'll let it settle out, and then you'll wash those crystals. But often, if you're really producing a lot of THCA, it's really effective to actually have a high capacity filter. So inside of here, we have a really long candle filter with a really large surface area, and actually during the rinse process, we'll allow the crystals to be washed out of the crystallizer vessel and deposit themselves onto this filter cartridge. It's a really effective washing technique because you're depositing them on the outside of this filter. You can flush with clean solvent and get the crystals really, really cold. And one challenge that exists in the industry is removing the THCA from solution. What we do is we can actually change this filter from cold to warm. And so what we'll do is after we've deposited all the THCA on the outside of the filter, we'll heat up the jacket of this filter and then flush with clean solvent, and we can redissolve them actually through the filter and back over to the crystallizer.
So in the end of the process, you've got concentrated, usually like 98, 99% THC isolate, and then you redissolved it back into the solvent, and it's either in this vessel or it's kind of redissolved in that vessel, but it ends up collected so that you can then remove most of the solvent vapor, right? And how do you get it out of the system?
Yeah, so there's kind of two ways you can eject it from the system. Actually, three ways. If you're going to be producing diamonds or growing larger crystals, we'll dissolve it and get it to the right saturation and then transfer it to a miner. But most often we're removing isolate from the system. If it's a relatively smaller volume, it can be all right to open up the 6-inch collection cab at the bottom and remove it. But often what we do is we'll redissolve it in ample butane, and then we will reduce it down until there's just enough solvent that it's a really thick slurry, and warm it up. And then when we eject it from the system, it essentially extrudes into a Cheeto-like consistency or a spray foam-like consistency and directly into isolate essentially that we can post-process and purge.
Lyndon, what's a way that people can learn how to implement market-leading crystallization processes like this?
So yeah, we host seminars periodically. Me and Murphy run the class and give people kind of a hands-on approach to various scales of crystallization. So people can come here and try out the system and also just learn about the process of crystallizing in general.
Find out if your extraction processes are leading the way by taking a free quiz. You'll get a customized report showing areas of strengths and also key areas that you want to focus on your journey to market mastery. Find the link to your quiz in the description below.